Let's now get back to the missing piece of our triangle Tonti diagram. So we've got the displacements at the triangle vertices, the strain in the triangle, the loads at the triangle vertices. The question is what goes in this circle down here? And let's call what goes in there by the symbol sigma. So for internal virtual work, we should be able to do the dot product of sigma and epsilon, the matrices sigma and epsilon. Now we know what that means. So for that to be even possible, sigma must be a 2 by 2 matrix, we know that. Sigma must be symmetric because epsilon is symmetric, and if the dot product of the antisymmetric part of sigma with epsilon would vanish anyway, so sigma must be symmetric. So we know that sigma must be a symmetric 2 by 2 matrix. Now, there are some calculations that are going to follow that are a bit tedious. So if you're willing to accept the deduction that comes towards the end, you can skip the part that says begin skip and ends with end skip, and then you can get beyond that. Okay, so let's do the tedious stuff. Internal virtual work, dot product of sigma times epsilon times the volume of the triangle. And we use our trace formulas from the previous video, basically the trace of a product of matrices. And the cyclic permutation doesn't change the trace. That's what we're doing over here up to this point. And then we recall that the side matrix, the side vector matrix dx, and the inverse of the side vector matrix. And we're doing some plugging it into the trace and things of that nature. So the internal virtual work so sigma times dx inverse transposed is 1 over 2a where a is the area of the triangle, times we have now minus sigma times n2L2 and minus sigma times n3L3. Now we plug this back into the trace and do some more calculations and reorganization, remembering that n1L1 plus n2L2 plus n3L3 is equal to 0 from the video on the properties of triangles. So using an assortment of these facts, we are able to collect terms and write the internal virtual work in this fashion. So the whole idea of doing this is so that we can group the terms in such a way that there's something multiplying the different components of displacement. So after all of this maneuvering, we get to a point where we're able to write the internal virtual work as something transposed the displacements at vertex 1, something transposed times the displacements at vertex 2, plus something transposed times the displacements at vertex 3. Now, internal work must be equal to external work, which means these somethings are nothing but the loads at the vertices P1, P2, and P3. So if you look at the triangle and look at P1, P2, P3, we see that sigma times N3 must be the force per unit area on this edge of the triangle. And this leads us to our deduction. Suppose we take a 2D continuum and cut it by a line like that. at a point x where the unit normal is n, and the line cuts the two-dimensional continuum into two parts, A and B. What this previous calculation says is there is a matrix sigma such that the force per unit area exerted by B on A at x on the surface is sigma times n. The force per unit area, traction, T equals sigma times n. This is what the virtual work calculation has allowed us to deduce. In fact, this is the definition of stress. So stress is a matrix which when multiplies the normal vector gives us the traction. This is the definition of stress. So for example, if we take an object and the surface of it has normal 1, 0, if we do sigma times n, we get sigma x, sigma x, y, and this gives us our familiar notion of normal stress and shear stress from undergraduate mechanics. So we've deduced a definition of stress that is consistent with what we understand from undergraduate mechanics.